Hello everyone, welcome to Marketing Research MKTG 457. This is chapter 17. In this chapter 17, let's talk about what is beyond the basic data analysis. We talk about a little more advanced topics for your information, okay, for your knowledge. And we can and much of that is just for your knowledge, basically for your further exploration if you want to, and will not be too much in the this put this way, I don't expect you to do this, to apply this in your group project, okay? In your group project, you just do what I specified in chapter 16 and before, then you'll be okay. In this chapter, let's talk more about the F statistics and the factorial design in ANOVA and the potential complexity of experimental design and post hoc comparisons and specific contrast when it's appropriate, and sequential chi-square analysis as useful tool in discovering meaning in big data decision trees. Okay. First, let's talk more about this. Uh, the more complex experimental design requires an alternative approach to the analysis presented earlier in the textbook, in the chapters before. Right? But all these analyses still use the general linear model, GLM, that we talk about, general linear model. Let's talk about the F statistics. Um, we know that in ANOVA, we use F statistic, right? ANOVA follows an F statistic, okay? And the basic statistic for ANOVA and for GLM is the F statistic, okay? The F statistic, like in regression, involves the ratio of systematic variance over error variance. Basically, F stat is ratio, systematic variance divided by error variance. Okay? The calculation of F ratio requires that we partition the total variance into two parts. Okay? There's total variance in the data. We step them into two parts. We said the variance when you use the sum of squares, right? Total sum of squares, which divide them into two parts, split them into two parts. The within group sum of squares and the within group sum of squares, the variations, okay? Or SST equals SSE plus SSB, okay? SST is sum of square total. SSE is sum of square error or within the group, and the SSB is the sum of square between group sum. Okay? So this is how SST is calculated. SST or sum square total equals the sum of observed values deviations from overall and grand mean. Okay, Xij is each individual, X times grand mean X 2 bars, okay, and X is the individual score, that is the ith observation or test unit in the jth group, okay. X bar is grand mean, okay. N is number of all observations or tests in a group. C is number of j's groups or columns, okay. That's how we calculate. We add up the differences, the square differences across all the columns and then across all observations. Okay, all observations within each column. So that's all observations. Okay, and basically F is the SST is computed by squaring the deviation of each score from the grand mean and summing these values together. Okay, that's SST. Then what's SSE? SSE is a variability that we observe within each group, whatever remaining after using the group to predict the observations. It's calculated by squaring the deviations of each score from its group mean and summing these scores. Okay? This is each score minus its group mean squared and summed up across all the columns and all the observations. That's sum square error, SSE. And then SSB is sum squared between groups, right? It's a variability of the group means about the grand mean. It's calculated by squaring the deviation of each group mean from the grand mean and multiply by the number of items in the group, and then summing these scores. Okay, summing these scores. Each one, okay, that's sum square between groups. Okay, that's SSB. Okay. And then how do you calculate your F ratio? You have the sum square between right here. The degree of freedom is between groups. The number of groups is C. Is column C. C minus 1 is degree of freedom here, right? And within group, sum of square is this equation here. The degree of freedom is Cn minus C. Okay. And then the total sum of square total, or SST, is this. The degree of freedom Cn minus 1. Okay. And then we want to calculate the mean squares. The mean square should be the SSB divided by its degree of freedom. That's SSB divided by C minus 1, give you mean square between. Okay. You use SSE, sum square error, divided by its degree of freedom Cn minus C, that will give you mean square error. Okay, that's mean squares. And then how is F ratio calculated? You take MSB divided by MSE to get your F statistic. Okay, that's how F is calculated. Then you compare that with the table, standard table. This one shows the general linear model F computation in JMP. You click on Analyze and the fit model to open the dialog box. You enter dependent variable in WAG and predictors here. Okay. And then output appears in a new window like this one. Okay, this one. This is JMP. ANOVA for complex environmental designs. Okay. A randomized block design allows the researcher to control statistically for the impact of nominal or ordinal control or blocking variables. Okay, when you have a nominal or ordinal number of variable or blocking variable involved, you can use a randomized block design to do that. Okay, to do ANOVA. Okay, so you can control statistically for the impact of that variable. Okay, the linear model for that. Is the mu y dependent variable, the independent through observation on the dependent variable. Mu is the grand mean. Alpha j is the J's treatment effect. Beta j is the ice block effect, and E is random error or the residual. We got the residual. Okay, that's the for randomized block design. Okay. To conduct ANOVA, we petition the total, petition, okay? We separate the total sum of squares, the deviations, into non-overlapping components, just similar to the F, right? The sum square total equals to just sum square treatments, sum square due to the blocking variables, and the error, okay? SS total is this. This is SS total. Okay. Okay. And then sum square treatment is the YJ bar is the J's treatment means, and Y 2 bars is grand mean. Okay, that's for that sum square treatment. And then sum square from the blocking variable, block sum of squares, the Y I bar is ith block means, and then Y 2 bars, double bar, is grand means, and this is your SS blocks. Okay, and then your sum square error is this. Okay, Yij. Okay, and right here, yeah, I can't go back. Sorry. Anyway, yeah. So the ANOVA here is, you calculate your sum square for the blocks, between blocks, between treatments, and error to come up with your sum square total. These are the corresponding degrees of freedom. Right? R minus 1, and columns, the treatment groups C minus 1, etc. Okay? This is the mean square. Okay? Then you calculate your F like that. This is your F ratio for the treatment, the mean square treatment divided by mean square error, and F statistic for the blocks is mean square blocks divided by the mean square error. Get your F score. Okay, then compare that. Okay. Next, talk about the factorial design. Right? A factorial design produces an experimental design fully implemented with 2 or more experimental variables. Observations are taken for every level of every experimental variables. And we can use a factorial design. A factorial design and one-way analysis variance and the multiple regression model share something in common. Okay? The sum of squares for each of the treatment factors, rows or columns, is similar to the between group sum of squares in a single factor model. Okay? And each treatment sum square is calculated by taking the deviation of treatment means from the grand mean. And determine the sum square for the interaction is a new calculation because this source variance is not attributable to the treatment sum of squares or the error sum of squares. Okay? Basically, for factorial experiment, you have ANOVA, Yijk is an individual observation on different variable. Mu is a grand mean. Beta I is a IC effect of factor B, that's a row treatment. Alpha J is a J's effect of factor A, column treatment. Right? I, there's a new one now. I, interaction effect of factor A and B. And then there's random error or residuals. Okay, residuals. And this allows for prediction of dependent variable based on changes in the mean due to factor A, factor factor X, factor F, and the combination effect of X and F. That's interaction. Okay. It can be generalized to K-way ANOVA, where K represents a number of factors involved. This is the partitioning of the sum square for two-way ANOVA. Okay, 2 treatments, A and B, sum square total, sum square of treatment B, sum square all rows, the sum square of C, treatment A, and the interaction and error. Okay, this is your sum square total. Okay. Okay. And then this is your sum square treatment B. The Y bar is the mean of the ice treatment for factor B. Y2 bar, double bar is Y total. Right? Overall, this is sum square C for treatment A. Okay. And then this is sum square interaction. Okay. Treat A, B, and the interaction. Okay. Then sum square interaction is sum square total minus sum square treatment B or A and error. You can do that. Okay. This is sum square error. Okay. Yij is the means of the interaction effect. Okay. That's you can calculate indirectly. Okay. This one shows a ANOVA table for the 2-factor design. For 2-factor treatment A and treatment B, okay, that's the degree of freedom. Okay, you have the interaction of A and B. Okay, that's degree of freedom. you can sum of square error, right? That's degree freedom and sum square total. Okay. From the sum of squares and its degree of freedom, you can calculate the mean squares. Mean square for treatment B is this divided by that. Okay. Mean square for treatment A is this divided by that. Okay. And mean square of the interaction is this divided by that. And for the error, the sum square error divided by its degree of freedom, that's this right here. Okay. Then you can calculate your F ratio. Right? You have three F ratios. The F ratios for the treatment B, okay? So F ratio for treatment A, and the F ratio for the interaction. Okay? You can compare to see if it's significant. Also, in more complex experimental designs, there's issue of within subject design and between subject design. Right? Within subject design and between subject design. What is within subject design? Within subject designs involve repeated measures because with each treatment the same subject is measured. They put someone, the same group of people, in the same, like remember the example I gave you, purchase intention on lighting and color of the room, right? You the same people, same group of people, same subject, under different colors of room or different lighting conditions. Okay, it's an elementary one factor within subject design could be analyzed with a paired samples t-test. You can do that. Okay, there is a demand effect though. Demand effect or demand artifacts. The demand effect or demand artifact. A demand effect results when the differences between treatment level could be caused by awareness of the treatments rather than the genuine response to the treatments. You put someone, in blue room, and then in the green room, and then in the red room, right? The person may realize, oh, you want to see the difference between different rooms, right? And then that's the demand effect. Okay, awareness of the treatment is not their true response to the color. But then they know that you're testing. That's a problem with the within group. That's why we want to use between subject design. Within subject design is called for a repeat measure for analysis. In each row, a data set is going to constitute an individual observation, whereas in each row going to constitute all observation on each subject. The two approaches here, right? The first approach would involve stacking individual observations on top of one another. Well, typically, these analysts do not stack the responses for repeat measures, and instead use one row to represent all measures for subjects. Okay, so by avoiding stacking, the data are in more of a user-friendly format for most statistical software, including SPSS. This chart illustrates the within and between subject design. Okay? Here, this is within subject design. The same subject is measured after being exposed to each color lighting combination. Okay? This is between subject design. Each subject is measured only once after being exposed to only one color lighting combination. As you can, there are different subjects here for different conditions. Okay, which one gives you a higher validity? Between subjects. Okay, between. Here's an example of repeated measure data in Excel. You can see the location there, the promo method, FB, PIN, or EM. I think stands for Facebook or something, doesn't matter. And the color, different color room. Okay, you see, for example, for FB, blue, there's FB green, there's FB blue, etc. Right? Red, okay, white, different colors. There's the sales numbers from each. Okay, that's the repeated measure data in Excel. There is also an issue of a balanced versus unbalanced design. Balanced versus unbalanced designs. Okay, A balanced experimental design is one in which approximately equal numbers of subjects are exposed to each combination of treatment levels. Okay? Equal number of subjects are exposed to each combination of treatment. Each treatment, you get the same number of people there, subject there. Okay? That's balanced. An unbalanced experimental design is one with unequal number of subjects per experimental cells. The number is different, right? Different number of people. In the extreme, an incomplete experimental design results in some empty cells, and then there's no one put under certain experimental variables. Then, okay, that could happen. So the incomplete design complicates data analysis in many ways, not the least of which is inability to analyze all interactions. If you don't have a number there, you cannot analyze the interactions. Okay, balance. This is the estimated means for promotion type and time of cells. Okay, this is cells period 1, 2, 3 versus estimated mean cells and the different promotions. Okay. The post hoc contrast. Yeah. The F statistic, cannot tell us which factors are statistically significant. Okay, and then we can do a post hoc comparison. We just know this that they're different, right? But we know which one is different, right? From which. So a post hoc comparison tests the statistical significance of all possible group differences between means. Okay, you do a post hoc way. Okay, and typically a post hoc comparison is made in exploring potential specific differences when no specific hypothesis addresses differences between specific groups. Okay, that's when you do a post hoc comparison. Okay? And perhaps the most commonly applied post hoc test is the Tukey honestly significant difference test technique. Tukey test. Okay? Post hoc contrast. Alternatively, one could use the fit model and allow a similar process but select multiple comparison to get the t-test instead of compared means. Okay? Fit model is appropriate for factorial designs. Several drawbacks limit the confidence that one has in post hoc comparison results. Post hoc comparisons have disadvantages in terms of both type 1 and type 2 errors. Okay? This is one example of a mean WTP by experimental conditions. Okay. Okay. Plan comparison. A plan comparison or a priori comparison, represents an alternative approach to examining specific difference between means of different effect combinations in ANOVA. Okay, the three key differences between planned contrast and post hoc comparison test exist. Okay, a planned comparison is appropriate when hypothesis exists ahead of time, specifying the specific combination expected to yield a significant difference. Right? When the planned comparison is appropriate when hypothesis exists ahead of time, specifying the specific combination expected to yield a significant difference. Okay? The analyst only tests the combination involved in the hypothesis. Okay? Therefore, it has the planned comparisons contain more statistical power here. Okay? Planned comparison. The combination of individual group means representing a planned comparison is known as contrast. Okay? Contrasts are created with arithmetics that specifies positive and negative weights to the groups or individual cells that will be compared. The positive and negative weights must sum to 0. Okay? Unlike the post-hoc comparisons, every planned comparison is independent of the others. Thus, no adjustment is made to type 1 error rate. Okay? Each test has a type 1 error rate of alpha. This researcher inflates the likelihood of finding a good result by chance. Okay? Mining data mining with the sequential chi-square test. When it comes to analyzing big data, market researchers work in very much of an exploratory mode. In mining big data, researchers work in very much an exploratory mode. Okay? Data mining is much more about prediction than explanation. Okay? The industry users, they just care about the prediction, whatever, the sales may be, whatever is more likely to be sold. Right? And they care less about, why that is the case, why that's the case. So data mining is much more about prediction than explanation, okay, Excuse me. The search focuses on identifying characteristics that have a statistical relationship with some outcome of interest. Okay? Automatic interaction detection refers to a computerized procedure that searches for variables within the data set that relate systematically to the dependent variables. Yeah. When you buy something on Amazon.com, for example, after you made the purchase, they give you some recommendations, and that is through this kind of big data mining. Okay? Decision trees. Right? This is often the output from automatic interaction detection comes from a decision tree. It's a graphical depiction of what-if analysis in a tree like program, tree-like diagram with the branches indicating the chances of some event occurring. Okay. Excuse me. There are software like chi-square automatic interaction detection or CHADE that forms a tree by splitting branches based on progressive contingency matrices. Software routine can create a decision tree in other ways, and CART is a classification and regression technique. It's called CART. Okay. This is an example of a decision tree for retail locations. Right? They use the chi-square test decision tree to test for different alternatives to find out the ultimate, the best result. Yeah. All right. I think that's all I have for this chapter, and this one is mostly for your knowledge, for further study if you want to, to give you a chance to know what is deeper in the field, what they're doing in data mining. Okay, and you're not required to conduct any kind of this research. This kind of tools, using any of these tools in your group project. Okay, for a group project, again, remember what I asked you to do. Your group project, after you collect your data, you need to do descriptive, correlation, ANOVA, chi-square, and regression, and that's it. Okay, all right, that's all I have. Thank you guys, and see you next time.